Alright, what's going on everybody? Today we're doing another LeetCode video. This one's called Lowest Common Ancestor of a Binary Search Tree. So basically for this problem, we're given a binary search tree from the root of the tree. And we're given two tree nodes, P and Q. And they basically want us to determine for those two nodes they give us and the tree, what is the lowest common ancestor between those two nodes. So basically what that means, like we can look at a few examples here. So for this first example, we're given the nodes that have the values 2 and 8. So these two nodes under this root node. So what would the lowest common ancestor of these two nodes is obviously going to be the 6, right? Because, you know, if we go down the tree either direction, like if the 2 is not an ancestor of 8, and vice versa, 8's not going to be an ancestor of 2, so it has to be the 6 here. It's got to be the root of that tree. So pretty straightforward example, but let's look at another. So let's look at the second one. So if we have 2 and 4, this one's a little bit less clear because, okay, so we're at the root here, 6. You know, we're always going to start at the root of the tree. Okay, so is 6, you know, what is 6's relationship, the current node we're at in the tree, with those two nodes, 2 and 4? Well, it's greater than those two nodes, right? So we're going to want to search the left half of the tree for the lowest common ancestor. So we basically go this way in the tree. Okay, now what is 2 and 4's relationship with 2? Well, we're at the node 2. So basically we can't traverse any further, right? And there's guaranteed to be an answer. So we need to return basically this node 2 here, because you know, if we go to the left, 0 is not an ancestor of either 2 or 4. If we go here, well, we're no longer an ancestor of 2, and a node, we can basically return either P or Q in the answer. So like if 2 is directly the ancestor of 4 here in this case, the answer would be 2. It wouldn't be like 6, for example. They want us to return that 2. That counts. Because here, the LCA of nodes 2 and 4 is 2, since a node can be a descendant of itself, according to the LCA definition. So important thing to note, we'll look at that example in the algorithm. Yeah, so let's go ahead and step through the algorithm step by step. So we're going to start at the 6 here. Again, you know, the nodes that we're given are 2 and 4. They want us to find the lowest common ancestor of 2 and 4. So we're going to start at the root node, okay, and we're going to ask, okay, is the value of 6, you know, how does it relate to 2 and 4? Well, it's greater than 2 and 4, so we need to search the left half of the tree. And by the way, I'm going to do this iteratively, so you can start imagining iterative code for this. So we're going to go to this 2. Okay, what is 2's relationship with 2 and 4? Well, it's not, 2 is not greater than 2 and 4. It's also not less than 2 or 4. So at this point, we've found the LCA, and it's going to be 2. So we would just return the value at this node. So yeah, let's maybe look at a little harder example. So this example is pretty easy. So let's look at maybe 0 and 3. Let's take 0 and 3. So 0 and 3, again, we're going to start at the root node. We're going to look at both of those values. How do they compare to 6? Well, they're both less than 6. So once again, we're going to go to the left. When these values are less than the node we're at, we're going to go to the left. If they're greater than the node we're at, we're going to go to the right. So anyways, we go to the left. Okay, is 0 and 3 less than 2 or greater than 2? No. It happens to be it's neither of those. It happens to be in the middle. So again, this is going to be the LCA. 2 is going to be the LCA because basically as soon as we get to be one of those two values, or we get to be between them, we know we're at the LCA. So that's pretty much the idea. The code is pretty simple, so I'm just going to get into that. So basically, we're going to say while root right? Because that's going to be, we're basically just going to use that as our temp node to traverse the tree that they give us. So while root, we're going to ask, we're going to say if the value for, so we need the value for the node at P. So if P val is greater than root val, and we also need to compare the value for node Q. So if Q val is greater than the value at root, then what do we do? What do we do when those two values are both greater than the root? Well, we need to go right. Or we need to go, yeah, we need to go right. So we're going to search to the right by assigning root to root right. So just that right child node. And that's how we're going to traverse to the right. So we need to do the opposite of this to potentially search for the left, right? So if the value of that target node, descendant node, is less than the root value, and the value of the other target descendant node is less than the root value, then we can search to the left. So same idea. And if neither of those conditions are true, we know we're either, at the parent that's like right between those, or we're going to be at one of those nodes. So long story short, if neither of these conditions are met, we know we've found the answer. So we're just going to have a else here, and let's change this to an else if. So this is just going to be the final else, and we'll just break. And then we can go ahead and return the value at root, or they actually want the tree node, so we'll return the tree node at root. So we'll just return root, and then that's going to be the lowest common ancestor. So that's pretty much it for the code. It's going to be, it's basically going to be big O of n time, or big O of log n time, or big O of h time, because the time complexity, we're just choosing one direction each time. So we're only going to have to do that as many times as there are levels in the tree. So basically, long story short, the time complexity is going to scale with respect to the height of the tree. So we can say big O of h time. In the worst case, if the tree was heavily skewed, it would really be like big O of n time. And the reason I said big O of log n time at first is because like the height of the tree is related to the total number of nodes on average by log n. But anyways, yeah, big O of log n time, technically in the worst case, like if you had a super skewed tree, which is possible. And then, but really a better description on average, probably big O of h. And then big O of one space for the space complexity, because we're just doing an iterative approach here and there's no extra data structures. So let's go ahead and run this. Hopefully this video helped you understand the problem better. If it did, leave a like and subscribe, and I'll see you guys in the next piece.